Now that we understand what the conservation laws are, let us just take a very simple example to demonstrate the conservation of energy. And that example is conservation of energy. We'll see how the energy is conserved when the object falls from a height. So let's just start this and first understand what does it mean by the free fall. Right? So in the free fall, there is an object which is placed at a height, and this object goes from the position 1 to position 2, and of course we have our ground here, and this object is moving down. Now we will try to understand how its energies is. There are two energies involved here. One is the kinetic energy and second is the potential energy. How they are actually changing, and we will demonstrate, we will show that the sum of the kinetic and potential energy is constant, which means that the kinetic energy at point 1 plus potential energy at point 1. Okay, so that is the total energy at this point, and the total energy at the second point is kinetic energy at 2 plus potential energy at 2, and these two we will say are the same. They are equal. Okay, so another way of writing this expression, that the kinetic energy plus potential energy remains the same, another way to write it is as follows. We say that delta KE, which means that the change in kinetic energy when the object goes from point 1 to 2 is plus delta PE when the object goes from point 1 to 2. So change in kinetic energy plus change in potential energy is 0. So the net change in energy actually is 0. So these two statements, okay, these two statements are actually exactly equivalent. They are the one and the same. They are the same way. They are the two ways of writing the same thing. Okay. So with this, let's just start proving. Let's just do some maths and prove that delta Ke plus delta P is indeed equal to 0. Now again we will draw our our one object at two different times. Okay, and this of course being our ground, we will never forget to draw it so that we understand what we are doing. Then of course we already said that anything here we will say is labeled by the subscript 1. So here for example height would be h1, velocity would be v1, and similarly at this point the height would be h2 and velocity will be v2. Okay, so now let's just see what the kinetic and potential energies are, and let's just write their expression. So we know that kinetic energy is half m v squared, where m is the mass of this body. So this body is of mass m. Okay, now this is the kinetic energy. What about the potential energy? You would say that it is also very simple. It is just simply m g h, mass into the acceleration due to gravity, which is g into height. So that is the total energy, right? This is not the change in energy. This is the total energy, total kinetic plus potential at any point. What about change in energy? Let's just now compute delta Ke. Okay, so delta change in kinetic energy. Let's just try to compute that. Okay, so we can compute it. Okay, 1 to 2 when the body moves from 1 to 2, right? So this is the direction of motion. Okay, we will remember that. Okay, because it is important. Now that of course we know would become half m is constant. Okay, half m remains constant, and change in kinetic energy is v2 squared, that is the final, minus the initial v1. Okay, very simple, right? That is what it would be. The kinetic energy would be we just did the final minus initial, and that is of course the change in kinetic energy. Very simple, not difficult at all. Now from here we see that we have squares of two velocities. Now as soon as we see squares of two velocities, something should come in our mind, and that is the third equation of motion. Third equation of motion actually deals with the squares of velocities. Just let's try to see what that equation looks like. So that equation is actually very simple. It's not difficult at all. The equation, the third equation of motion, what it says is Vf squared, that is the final velocity, is equal to initial velocity, the square of initial velocity, plus 2 times acceleration. Okay, and in brackets, what is there? Distance is there. So it expresses the velocities in terms of acceleration and displacements. So my final displacement SF minus my initial displacement SI. Okay, so that is what it is. So that is the equation which relates the squares of velocities, that deals with the squares of velocities. So we will use this equation. So what is our V final? V final is of course V2, we know that. So here we will use V2 squared, and that is equal to V1 squared. And of course this G, the acceleration due to gravity is G, which is in downward direction. So this is negative. So we will just use minus sign here, and we will just use G. And S final is, of course, we know what is it. It is H2 minus initial was H1. Okay. So very, very simple, not hard at all. Okay. Now what do? I simplify a little bit more. I take V1 to that side, and this becomes V2 squared minus V1 squared. Okay, and I put it in square brackets. We will see why in a second, is equal to minus 2G, okay, H2 minus H1. So this is the our something that we have come up from the third equation of motion. Now these two quantities, V2 squared minus V1 squared, V2 square minus V1 squared, it appears here also. So we can simply do some substitution, and then we can come up with delta KE 1 2, okay, when the body moves from the 1 to 2, is equal to half m into V2 minus V1 this whole square. So I'll replace it with this one, which is minus 2G into H2 minus H1. H1, very, very simple. Okay, not hard at all, very, very simple. Okay, then this 2 and 2 would cancel, and this will become minus mg into H2 minus H1. Very simple, not hard at all. Like I said, very, very simple. Okay, so this is what it comes down to. Okay, and since we know that H2 minus H1 would be negative, okay, because our height is actually decreasing, so this H2 minus H1 will be negative. So one negative would come from here, second negative would come from here, and the total, essentially this delta KE would become positive, which we know because the energy is actually increasing, right? So we know that energy is increasing, and the change in kinetic energy should actually be positive, because sorry, not the energy, the kinetic energy is actually increasing. As the body is falling, its velocity would be increasing. So this delta KE should be positive, and it will come out to be positive because H2 minus H1 is negative, and we have another negative here. So negative will become positive. Okay, so this kind of makes sense. We know that it is making sense. What about mgh? Delta P. Okay, so change in potential energy, now we will come to that, is equal to mg, again remains constant because that is indeed the case, into H2 final minus initial. Okay, now what about delta KE12 plus delta KE12 plus delta PE12. If I write them together, this H2 minus H1, this H2 minus H1 is the same, but the sign is, this is negative and this is positive, but the other magnitude is exactly the same. So this comes out to be 0. So with this, we have shown very simply, without using calculus, just by using the third equation of motion, that the change in kinetic energy is actually a change in the total energy. Kinetic energy plus potential energy is actually 0. Kinetic energy would increase, whereas the potential energy would actually decrease, because this H2 minus H1 would turn out to be negative when the body is going down, and it would be inverse when the body is going up, which kind of makes sense. We understand that the potential energy should decrease when the body is going down, and the kinetic energy should increase. Very, very simple. Now what about if we want to do the same thing with calculus? Now we will do it this time with calculus. So things become even more simpler in this case. So in this case, what happens is, again we write the same thing. Okay, so we will say that kinetic energy plus potential energy, okay, we will just write them, we'll just give them another two terms. We will call KE as T and we will call PE as U. This becomes T plus U, and this of course we know is equal to half mv squared plus mgh. Okay, this we know. Now what about change in kinetic energy? So this becomes dt with time. Okay, so this is what we are concerned with, right? As the time evolves, how do these quantities change? So this becomes half of mv dv by dt plus mg dh by dt. Okay, so what I have done is very simple. See, half m is constant, okay, and sorry, I forgot a 2, and this v squared, when we will differentiate it, we will get 2v dv by dt. Okay, so this is the differentiation of v square with respect to t, and when I differentiate mgh, mg is constant, so it comes out, and dh becomes dh by dt, which is the rate of change of height with respect to time, and dv by dt is the rate of change of velocity with respect to time. Very, very simple, not difficult at all. So far the concept is very simple. Okay, so again this 2 and this 2 would cancel. So here we will get mv dot dv by dt plus mg dh by dt. Now think about it for 1 second. Okay, see, dv by dt and dh by dt. Okay, so if you remember, our objects are falling like this. So we are going from 1 to 2 and the object is going like this, and then we have the ground here. Okay, so our object is going like this. Okay, so this is something we understand. So we are saying that the height is actually decreasing. That is something that we are seeing. Okay, and if the height is decreasing, the velocity is actually increasing. So one of these would take negative sign, dh by dt. You can pick whatever you want. Okay, either you can make this negative and this positive. So either dv by dt would be negative or dh by dt would be negative, but those two would have opposite signs. Okay, so we will just use the convention here. Okay, and we will say that this is mv dot dv by dt is just the acceleration which is due to gravity, which is g, minus mg, just dh by dt is actually just the velocity. Okay, dh by dt is nothing but the velocity. It is just the change in height with respect to time, which is the speed. In this case we can take the speed also, because we know that everything is happening in a single direction. And similarly dv by dt is just the velocity, it is the rate of change of velocity, which is just acceleration, which we know to be the acceleration due to gravity. So I took the sign of this v to be negative, and this dh by dt becomes minus v. That's what we said. And of course this mgv and this is mgv, so these cancel out and the answer comes out to be 0, which we would expect. This is the change. Okay, so this is not this, but this is essentially the change in d of dt of kinetic energy plus potential energy. Okay, the rate of change of energy, and this comes out to be, as we said, it comes out to be 0. So we've shown that the change in kinetic energy plus change in potential energy in both these cases, whether we do it with calculus or without calculus, is always equal to 0, which we would expect from the law of conservation of energy. The change in energy should actually be 0. It means that the energy remains constant and the total energy does not really change. Very, very simple.